Welcome to whatever this is. Now, I don't know quite what you want, but I'm going to take everything I know, transfer it onto you. So maybe you'll do something with this. Maybe it'll be useful. I don't know. But first off, what is this thing? What is electricity? What is this? This is the nucleus, okay? And this are electrons. It is the flow of electrons through something called a circuit. Now, if we go to, I'm just going to do this on Tinkercad because it's easier. Bodacious Blad. No, we don't do that. Okay, I found an actual editor. So, schematics. I'm assuming this is what it's going to test you on, because I think you're on some type of electronics thing. Is the power source. It'll always be marked like this. It's a small line, big line, small line, big line, as you can see here. Now we gotta learn stuff, okay? I'm sure you've heard of positive and negative. You've connected something to a battery before. I'm sure you know how this kind of flows. It goes negative to positive, but there was something called like I don't know, we were dumb back then and we thought it was positive and negative. So that's what all the schematics, the conventional, it's called conventional flow. It'll show you positive to negative, which electrons, electricity, I don't know how they didn't see that. They thought it flowed. Yeah, they were pretty dumb. But that means if they bring up something like conventional, it's just. Now, how does electricity actually flow? So I'm sure you've heard of AC versus DC. These are heavily based with magnets, electromagnetism. This is kind of how AC is made. So AC would be used in something like your speaker, and yeah, you can see it goes positive and then flips. It flips the polarity, it keeps flipping it. So it's just, the electrons are just going back and forth, but that also creates electricity. Oh wait, DC is just the one-way direction, so it'd just be a straight line. And this is what AC looks like. Woo, 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 woo. DC is straight, AC is bi. Okay, that's how we're gonna learn that. You gotta remember, DC is straight and AC is bi. That's the only way. The reason I always get these confused is because anode means negative, okay? And I, in my mind, represent anode with add, positive, but it is the opposite. Anode add is negative, and cathode is just a weird goddamn word to begin with, but it means positive. So I'm sure if you flip a light switch, it's an open circuit, which means it can't be completed, therefore no electricity flows. Let's talk about resistors. We like those. So in this scenario, we're going to think of electricity as water, which is not at all what it actually does, but we're going to think of it as water. This will make, the more you learn about this, the more it will make sense. But for right now, we're going to think of voltage. Oh my god, that's so small. Voltage as the kind of the initial amount of water. And what a resistor does is it takes that and it constricts it so there's less voltage going through something. Now this is important because say your LEDs, they run off of they run off of electrons going through them at a specific frequency. I like this diagram the best because it's very simple. So it takes it, passes through a LED chip. LED stands for light emitting diode. Now it spews out electrons at a specific frequency to get the different colors. So like red takes the least amount of electrons passing through it. That's why it has the least amount of voltage. And say like white needs the most amount of electrons passing through it to get higher on the I don't know, light chart. I don't know, the fancy light chart. Passes through that LED chip, emits the light, then it goes out back into the anode. Now another thing we're gonna hear is current. Current is tricky. I don't like current. That's why water is so kind of weird. Electron go burr really fast through it. It's the concentration of electrons going through a wire. Yeah, the rate, I don't like the rate because that implies speed, and all speed is fixed through electrons, but like it all flows the same. If you take a really small wire and you pass so there's not a lot of room for the electrons to go, it's going to heat up a lot, because what's happening is the electrons are constantly bumping in to the protons and neutrons, and they're heating it up. But if you have a really big wire, and say with a lot of voltage and a lot of current, it'll be fine, because there's a lot of room for it to go. That's why your current is tricky. I don't like current. They don't explain it very good. None of these videos explain current quite right. Now, if you've heard the phrase, it's not the current that kills you, it's not the voltage that kills you, but the current, it's pretty wrong, because how's the current even going to get in if you have low voltage? Like, you need combination of current and voltage. That's why you can't like go around touching generators, because they got both. They'll kill you. So I found a good diagram on how a resistor works. So a resistor uses usually carbon fiber tubes with holes cut in them. Now this is kind of information you just need to know. Like say a 4-band code, the last two, this would be the multiplier. So yellow would be the multiplier. This is the first digit, the second digit, and this we don't care about because tolerance is just kind of like how accurate is it. So if it's 5% off, if it's 10% off, they're kind of misleading because you can't get everything in a picture. But yeah, so this would be 5. Then we've got to find blue. 5, 6. Oh, multiplier 10. Oh, okay. I didn't see that. I'm blind. But yeah, just multiplier, and then if they have more, it's you take whatever the last two and subtract it from the total. So just to get the regular digit number, so you take these two, subtract them out, and it'd just be these three color bands. Get one of these on your binder. Okay, this is what you need on your binder. One of these. How do you like kind of put this into the real world? How would you take the amount of voltage from something and apply it to, say, a circuit? Well, I'll tell you how. Ohm's law states that R is equal to V over I. I is current, by the way. So, where's my cursor? Let's say you have a 9-volt battery, and you need to power something that is... This is how you find the LED for everything. You look at something called the data sheet. Like, you look at a data sheet for... It's really boring. I just look up on Google, because Google knows. So, between 3 to 5 volts. We're going to say 4 volts. It's 4 volts to power this LED. Now, if you power it with less voltage than the required, it's gonna be fine. Like, it's just gonna be a lot dimmer. But if you power with more, it'll explode. Not in the fun way, just I don't know, just kind of stop working. 20 mA. mA just means, so A equal milliamps, so just 1,000 less than an amp. Yeah, like 500 for generator. Ampere, pretty high. So 25 milliamps. And again, you can just find this on the data sheet. I forgot the forward voltage, which is why we did that thing in the first place. So it's minus 4 volts. Forward voltage is just how much the LED eats up. That was a good arrow. How much the LED will eat up. 0.002. 2,500 ohms. Who is ohm? It's some dead guy. This is my desk. This is the breadboard. Now, breadboard works by connecting. So this positive strip you see here, this positive strip is all connected. This negative strip is all connected. And these are the rows. So that's a row of 5, that's all connected. Then you go to the next row, row of 5, that's all connected. And they're all separated by insulators, which won't allow any electricity to flow through them. So I said I needed a 25,000 ohm resistor. I have that somewhere, I just don't know where. Mine are cool because they're labeled, but you know. And how you can tell the polarity of the LED, the positive is larger than the negative, or the, I don't know, cathode is larger than the anode. Resistors do not have a polarity, so this should work. Now, connect positive. You can see the LED, right? Yeah. Just get rid of that. Yeah, you can see that. You'll see what glows. Positive to positive, negative to negative. It works. And it didn't blow up. That's great. With the 9 volt, to be honest. So this works great. This is Ohm's law, doing what it's supposed to do. Now, it could be brighter. If I made the resistors lower, which I don't want to blow it up. Now, this breadboard is really cool because it allows you to do electronics without having to solder. Soldering is no bueno. I don't. The multimeter. This is a great thing that allows you to measure the resistance of something, the voltage of something, or the current of something. So you can go measure the battery, or I don't know, do all these calculations without using a data sheet. It's pretty cool, you know? I'd suggest the one that does it for you, the auto one. I don't know, these things are really expensive. Oh my god, get a digital. Oh my god, these things are expensive. You like this one, something that's really cheap. Let's talk more about schematics. Now this is the boring, the most. I have built entire circuits without using schematics even once, but I guarantee you they're gonna test you on this. I guarantee you. So let's make that circuit I just made, but with this. This is just a random one. I'm not gonna measure it. Like if you I accidentally connect the positive, it's fine. Doesn't really matter with resistors. But LED. Oh shoot, that's wrong, isn't it? Bye bye. Yes. It's pointing towards the positive. This would be my circuits in schematic. I find schematics to be extremely boring. Voltage go. This is my favorite thing electronics I'm going to talk about. Have you ever wanted to do a button So with the buttons I have, they have 4 pegs, and they have a button. Now what this does is when the button's not pushed, it creates an open circuit. So when, say, I don't know what these two are for. I just don't use them. But yeah, when I just use it as kind of like a switch, but it's a button. It takes the negative side and prevents it from the positive side. That's all a button. It's not complicated. Button don't go, it don't go. Button go, it connects, and then it can go. Kind of the same thing with switches. No go, then switch, go. What this means is I'm gonna do the single throw, double switch on something. When you have, say, two switches, what a throw means is just when you hit it and press it, you have these connected, and then you go down, and then they're on, and then you go up and they're off. That's kind of the same logic which applies to pretty much all of the. I don't know if they'll test you on this though. So the fancy term for power is wattage. Just like power in physics is joules, it is the ability to do work. That's pretty much it. Like equivalent to a joule. It's the same thing, but in, like, I'm sure you know what a joule is. Same thing here, just with power, just with electricity. Now it pains me to talk about parallel. Resistance and parallel do not go correctly. I don't like parallel because of the resistance. So here's my understanding of parallel. I'm cutting all that other stuff out. Parallel is, while series affects voltage mainly, so like you can put a resistor and affect the voltage, parallel affects the current. That's why I don't like parallel, because it is so confusing for no reason. Now, I think if you put a resistor in one of the branches of the LED, that's an LED, and you hook it up so, like, this is the only way it can flow, because that's what a diode does. It only lets electricity flow one way. It'll get the same voltage, but that's not for everything, because of the kind of this rule where the resistance in the total amount of current is 1 over R plus, like, 1 over R1 plus 1 over R2. So that'd be like R2, and this would be R1, except if there's a resistor right here. I think that just affects the total amount of voltage, but the current remains the same for each LED. Like, so to find out the current of this, you take, say there are 2 LEDs, it'd be the I guess initial current, so current initial or whatever, divided by the 2 LEDs, so divided by 2, I guess. Now is finally a time we get to the fun part, which is explaining what each of these little things do. Let's start with capacitors. I'm sure you've heard of capacitors before. So capacitors are special in that they have polarity, which is a positive and negative, and farad, yeah. So it just means same thing as like the voltage rating, pretty much, in ohms, capacitance rating. So the same thing as like the ohm. I don't know. There's a bunch of fancy math with this. You can just look it up. Mostly you can look it up. The only thing you want to know about these is they have a voltage limit. And if you exceed the voltage limit, like you can see on here, this one has a voltage limit of 50 volts. Don't exceed that or it will blow up. These will actually blow up. These have been known to blow up. I'm not going to blow this up because I don't have 50 volts on me, but you know, if I had a transformer I could. So this one might be a little bit too big for what I'm trying to do. What capacitors do is they charge electrons. They basically store electrons, and then when you disconnect the circuit, it'll still run for a little bit because these will release them back in. I was trying to show you it, but this is 50 volts. It's a bit too big because I'm only using a 1.5 volt one, so it's charging way too slow. The good old potentiometer. This thing is a potentiometer. It spins. You can see that. It can spin. Yeah, this thing, it spins because it changes in resistance is what it does. Okay. So, it works by having so say you want to connect like negative to here, the electrons will jump here, and since this is kind of like it's not conductive, it's a lot more resistive than the metal wires, it will so this acts as basically a giant resistor. Now you can adjust the resistance by adding this little wire, which the electrons will jump here instead and go out here. So that's how it kind of changes the resistance that way. This is a diode. It lets electricity go one way.
Wow!
That is all it does. Okay, now we're gonna go with relays. Relays are, I guess they use electromagnetism. They use something like that. They got a giant coil. It produces magnetism, and it pushes this. It's used in like automatic switches and stuff. It just pushes it and it switches it.
Now watch me nay nay. Okay. Now watch me whip. Watch me nay nay. Now watch me whip.
Now transistors are like the better relay. Now what a transistor does is it takes the it's a switch, but it's kind of a more complicated switch in that right here it takes like say 0.6 volts to actually like let current go through. You see that? But it has to be, so you'd have to take this to a different power source. So in that way you kind of create a I guess you say a more complicated potentiometer is what a transistor does. So you can change the voltage to get like say half current going through it or stuff like that. So it's more, this is more current based. You can do a lot more with transistors. This is kind of like, so this is used for, I guess, speakers and microphones and stuff like that. So transistors are used for lots and lots of stuff. You can look more up on what they're used for. Now, with integrated circuits, this is where the real fun begins. These circuits kind of combine everything from, I guess, like capacitors, well, not really potentiometers, but they, especially transistors. Like this is like main use of transistors. It's used with, say, resistors and stuff like that. So this is called the 555 timer. It basically just makes blinky light. It makes blinky light. But it takes, here is where power comes in. It's called VCC. This means, it's really weird. This is positive and this is negative, even though this is where this is where the positive to negative flow comes in. So power comes in here through these resistors. Try and look. I'm not too sure how the integrated circuit works. There are a bunch of different kind of circuits. Well, obviously there are a bunch of different circuits that do different things. So I encourage you to look up how this works, like, and look up an actual cool video on how this works, because I cannot tell you. But integrated circuits, they just combine everything. Which brings us on to our next portion of the video, the microcontroller. This is the same thing as an Arduino. It's just cheaper. I'm also getting a 3D printer made by the same brand. It's just cheaper. It's the same thing. It is fine. This is the Arduino IDE. IDE just means like coding platform thing. I don't know. It's code thing. Now, what this does is it takes the code that you write and interprets it into the Arduino board. Okay, here is the code that I totally didn't steal. Don't look at that. This is written in C++. Well, not in C++. It's based off of C++. It is, I don't know, you have to have a little bit of coding knowledge just to use it. I just look all my stuff up. I just found that on a forum, so that's literally all I did. Like, if you're gonna use this in actual tournaments, I would download like I'd just watch a tutorial on how to code in C++, because it's basically the same thing. It's C and C++. It just uses a bunch of libraries. Oh, it's include, and then see how it goes green. Include servo. Servo is just a library which operates a servo. Manage libraries. Manage your libraries. You can find your libraries. You can do whatever you want. On the Arduino, on the actual Arduino, there is a ground pin and a 5-volt pin. Connecting these circuits, there's a thing called ground. You can see that. It's the highlighted thing. That is negative. And then there's another thing. It's either going to call VCC or just 5 volts. That's the positive. Yes. Okay, and as you can see, with this code, it works. So I think it automatically sets the voltage to, through these pins, 5, which, why is this working? I don't know what voltage. I want to say it has an automatic sensor, but I don't know, because it has pin numbers instead of voltage counts, or like actual voltage. So I'm just assuming that pin 13 was the positive, and that was it works. It works anyway with this code, and as you can see, if you want to change the like how much it blinks, so you change this to 500. These are measured in milliseconds, by the way. Just these those things. Upload it. It blinks a couple times. Now it goes faster. And you could make this even smoother with a capacitor, but I'm not hooking that up because I am lazy. Okay, so that was just one example of what you can use microcontrollers for. You can also use them for DC motors. DC motors just use direct current, or just direct current to, and they employ like magnetism. My God. Electromagnetism. Sometimes. God damn it. Anyway, DC motors. They employ electromagnetism to turn the thing. Since current is only going one way, it's a lot simpler to turn this. Electrons flow through certain coils at certain times. So if I can find a good diagram I can show you, but there's like nothing here. You'll go, it turn using magnet. The only thing you need to know is it turn using magnet and coils, and it only lets electrons flow through stuff at certain times, so it gets the full rotation. So that means if you reverse the polarity, it reverses the zoom. Yeah, they use a gear system. They literally use a DC motor, but they use a gear system, and then they're a lot more accurate. That's the word. They're a lot more accurate. That's about it about servos. They're just resistors, but if you shine light at them, they get more resistor, and then when there's a lot less light, they're less resistance. They can use transistors with photoresistors, so they it kind of like cuts off the it limits the amount of current, or I guess voltage going through it. So that means it cuts all this off when you shine a light on it, and then when you don't shine a light on it, it's all good. It's all good. The trans. Yes, this takes the low voltage and transforms it into high voltage, which is what you need for electricity to break the resistance forming in the air, because everything has a breaking point, even your skin. You might see this design too. This design with all the cuts in it just helps it reduce the heat and like makes it better. Okay, so what this does is it takes it in a low voltage, and since you can't really, since to the goddamn law of conservation of energy, you can't just create voltage out of nothing. What this does is it takes the amount of current, it takes the current of these of the starting electrons and transforms it into voltage, making a way higher voltage than you started off with, but a lot less current, a lot less. So this also works in the opposite with a step down transformer, which is what your house uses. So this takes the high voltage and transforms it into high voltage low current, and makes it into low voltage high current. That's all this really does. It doesn't really do much else. But yeah, this is how. So when you're in prison, you can just use this to make a taser. It's pretty cool. 30 kilovolts. So that means, yeah, 30,000 volts. So you'd need a couple of these in series to actually break air. They're just losses. These are just because everything's conductive pretty much. So all the eddy currents do is they circle and make it worse, and they turn it into heat. Yeah, some garbage. I'm sure there is. It doesn't really matter though. You just have to know if it's there or not. Okay, so I hope I answered all of your questions. If you have any questions, be sure to tell me, because this was a very quick run through of everything, like everything that I learned so far. But I can't. So now that you have a better understanding of what questions to ask, do your own research, because I did not cover everything. I know I did, and I know I can't, because I gotta get this video out sometime. But yes, do your own research, and I hope this explained everything. If it didn't, you have a question, I'm gonna say leave about down below in the comments, just because I'm like making a YouTube video right now and it's pretty funny. But yeah, bye bye.